have to, we need more information on CO2 because this is the triggering of growth depression, and that maybe the growth potential is not in all the farms as good as expected. So when we have kind of a mind experiment, and we have a feed load of 0.5 kilograms feed per cubic meter of stocking volume, which is a kind of an average one. It's not really high, it can go up to 1.5, I guess. And there's no flow between the tank and the water treatment system, because we have a decline in oxygen and increasing ammonia concentration. And we will base a little bit in the next slide on this ammonia concentration, because it's a good example how to simulate that, and a little bit to describe what is the need, especially in terms of water separation. But there's one important question: how do I model the removal of excreta from the fish tank? That's a really important information. And everybody knows the round tank design, and it's always addressed as a kind of self-cleaning device that you, in the center of the tank, you have an aggregation of the solids and the excreta and so on. But this is not the real story. The real story is that you have a lot of turbulence in the tank based on the activity of the fish. So what's going on is that this system is a totally mixed system. And this is really important to know when you go into the mathematical simulations. And you see that in this slide pretty well. So we have two models. It's a plug flow model. So in the plug flow model, there is the assumption that there's no mixture in the tank at all. Then you have the completely mixed system. So all the water going into the tank is completely mixed before it's going to the outlet. This is a different mathematics behind, and you see that there's a rule of thumb that a water circulation rate of 1 per hour, which was enough in the past, but this is assuming that you have kind of a plug flow model, and this is not true for many tank designs. So in a completely mixed system, it's probably the other side. Of course, it's something in between, but if you do a completely mixed flow model, you see that you have to increase your flow rate up to 4 times per hour to have the same exchange of excreta per hour in the tank. So then you reach almost 100%. So that's why we see a little trend in today that most of the systems, they go to a circulation rate of 2 to 4 times per hour. In shallow stack raceway systems, they probably have even 8 or something like that. So if we go with this kind of modeling and we just increase the flow rate and we look at the ammonia concentration starting by 0, and then we feed the fish 12 hours a day, typical feeding cycle, that's why you have this duality in the graph. And you see that, of course, ammonia concentration is going down when we increase the flow rate. So fish is excreting ammonia, and the biofilter is oxidizing the ammonia to nitrate. So in the equation is also, that's why in the equation is also needed the size of the biofiltration system. And that's also interesting just in the same mind experiment with just a circulation rate of 1 time per hour. You see that the biofilter can be too small, then we have kind of limitation in the oxidation process, but it can be also too big. Yeah? When the biofilter is too big, what it means, then we have a really long retention time of the water, and the ammonia is oxidized and it's almost by 0. And when it's by 0, you see that here in the next slide. Of course, if the ammonia concentration is 0, there's nothing to oxidize. So then the removal rate is almost 0 as well. So to achieve high removal rates or oxidation rates in the biofilter, you have to increase the ammonia concentration. But if you do this, then maybe the biological limit is exceeded, you would expect. So we see a limit as in our farming systems at 1. Yeah? So that means that we have maybe a removal rate of ammonia of 200 grams per cubic meter a day. So there are much higher rates possible, what you see also in this graph. So what to do to increase at an ammonia level of below 1 our oxidation rate in the biofiltration system? You have to increase the flow rate. That's the only way to do this. And this is the slide you see on the right side, where we just have on the x-axis the tan load instead of the tan concentration. Yeah. So this is again an example, an easy example, how you can see that an increase in flow rate is optimizing the system. And when we compare this on the ammonia concentration, inlet and outlet, you see at the circulation rate of 1, what we see? We have a high difference in the diurnal rate during the day. So we have a maximum time concentration in the midnight, usually, and then we have a low one in the morning hours before the feeding cycle starts. We see also that we have a big difference between inlet and outlet concentration. And now we increase the flow rate to factor of 4, and you see a big difference. So the difference in inlet and outlet concentration is reduced. The absolute ammonia concentration is reduced. You see that the diurnal cycle is also reduced between min and max. So it's a really basic element, the hydraulic retention time or the flow rate. It's a really important tool in the RAS. When we base this information now on the water renewal rate, and you see this on the x-axis in percentage per day, and we set, let's say, kind of a limit for ammonia to be below 1, then it means when we have a water renewal rate of 2000% per day and more, we don't need anything. It's kind of a flow down. And if we want to decrease now the water renewal rate, of course, we need additional technology like the biofilter. And maybe the biofilter, not maybe, the biofilter is producing nitrate. And the question is, what is the acceptable nitrate level? So this is not, a lot of indications, different indications for different species, but we, for instance, we work with below 50 in our farms. 100 maybe nitrate, nitrogen is, I think, quite accepted for many. And it means when you have a water renewal rate below 15%, you need a denitrification. Otherwise, you can't remove the nitrate. So very often I hear systems, they claim they are closed RAS. That means below 10% a day. They don't have a denitrification. And I wonder how this can be. Yeah, it's denitrifying elsewhere. Yeah, and that's a common answer. And of course, it's happening, but it should not happen like that. Because this means that are uncontrolled areas you have in your system. And this is exactly what we have to avoid for certain reasons, like off-flavor, H2S control, and so on. I put this video to my talk because it was not so much about feeding in the session. You see our robot system here. You see that the fish is following the robot. The robot is distributing the feed during driving, so this is really excellent because no fish can really know where the paddock is going on. So we get a really good size distribution in the fish. We also have kind of a good distribution horizontally of the feed, and we gain high feeding frequencies. So it's not labor intensive to have a robot. That's why we can do this. So in our shrimp farm, we have a feeding frequency of every 5 minutes, 24/7. For the grouper, for instance, we have every 10 minutes. And when we use robot systems, sometimes we have charging times, so we move maybe from 10 to 20 minutes. In the grouper, we even started to feed the fish during daytime and nighttime. So nighttime means it's not total darkness, so they still can see something. This is also quite promising. So we have this diurnal cycle, but we feed 24/7. So why we do this? We have a more average feed load over the day. This is eliminating CO2 peaks, O2 drops. And what's the big problem also, when you have more fat in the pellets, you can have a negative effect on the surface tension in the water, which complicates ozonation, oxygenation. So it's more easy when you have a higher feeding frequency. This is a rendering of the new design of our Oceanloop farms. So following the same what you have seen in the video with some changes. We changed a little bit the geometry. We have seen the need of a portal crane to assist the operation in terms of shift